This is multivariable calculus, and in this video I'm going to talk about section 15.9, triple integrals and spherical coordinates. So we've talked about triple integrals for the last couple of sections, and last time we talked about triple integrals in cylindrical coordinates and just talked about some of the advantages that sometimes show up when you want to work in a different coordinate system, and advantages working in cylindrical coordinates where in a lot of cases when we had things where we sort of had an equation or a function that was easier to manipulate from a cylindrical coordinate perspective as opposed to a rectangular coordinates perspective. Sometimes the integrals can be very easy to solve in one form and not so easy to solve in another. So what we're going to look at today are spherical coordinates, which kind of the same thing again. We're just looking at particular situations where spherical coordinates might be more advantageous. So when we talk about spherical coordinates, remember we talked about the basics for this back in the first semester. So there is going to be some general knowledge here that I'm going to be expecting you to know that you may need to review a little bit at the beginning of this section about how to represent things in spherical coordinates. We have rules that are going to allow us to go back and forth between the rectangular coordinates and the spherical coordinates. And we'll talk briefly about that, but for the most part, I'm going to expect you to go back and review that if you need to. Okay, so the whole idea behind this is we're still trying to solve triple integrals. And for the most part, we're going to talk about this from the perspective of volumes because we're talking about the basics of triple integrals in spherical coordinates. So when we talk about this, remember in spherical coordinates, we have three different ways that we're going to reference a point in space. We have rho, which is essentially the radius from the origin or the center point of my sphere. We have theta, which is the same thing as what theta is when we're working in cylindrical coordinates or polar coordinates, where we're measuring off of the positive x-axis counterclockwise around in the xy plane. And then the last one is we have this angle phi. And remember, the angle phi is measured clockwise off of the positive z-axis. And that's the one that's a little bit different. Okay, so when we evaluate this, we still want to be thinking about our volume as a bunch of small chunks of volume that we're going to add together. So remember when we were working in rectangular coordinates, we had true rectangular prisms that we were adding up where we had a dx, dy, and dz as the three dimensions. Well, when we work in spherical coordinates, we're still thinking of these as tiny rectangles, but they're a little bit different. We're thinking of them as what we call these spherical wedges. And since the dimensions are so small, we can essentially treat these as if they are rectangular prisms. Now, to get the dimensions for these, it's a little bit tricky. And this is something we're going to go through in a little bit more detail in class. But the main thing here is we've got three dimensions. And the dimensions that we're looking at when we evaluate the volume of one of these wedges, we have delta rho. We also have rho delta phi. And we also have rho sine phi delta theta. Now, like I said, we're going to go through the details of that a little bit more in class, but the main thing is we can come up with those by thinking about how much these things change as I have a change, for example, in phi, or when I have a change in theta, what's happening to these dimensions of this wedge that we're essentially treating as a rectangular prism. Okay, so knowing that to be the case, then I can get the volume of one of these pieces by multiplying those three dimensions together. And in the end, here's what we end up with. We end up with rho squared sine phi, d rho, d theta, d phi. Okay, so now when we convert over, typically what we're going to be doing is we're going to be working in a rectangular coordinate system. We're going to convert over into a spherical coordinate system. Keep in mind, just like when we were dealing with our cylindrical coordinates and we were always multiplying by an r value, well, in this case, we're always going to multiply by rho squared sine phi. Okay, so keep that in mind whenever you set up those integrals. You've got to multiply by that rho squared sine phi when you convert from a rectangular system into a spherical system. Okay, so then the only other part of this will be how do we find our limits of integration? And similar to what we've looked at before, it's kind of an intuitive approach. We just have to remember what the three dimensions are actually representing. The rho is the radius from typically the origin. So the theta is measuring counterclockwise, starting from the positive x-axis, and then phi is measuring clockwise, starting from the positive z-axis. Okay, so there is a little bit of review in this section. You'll see when you go through the beginning part of the homework assignment, there's going to be a little bit of practice with converting from rectangular coordinates to spherical coordinates, which we've done before, but this is just a reminder of those conversions. And we talked about that back in the first semester, why those work the way that they do, but you can go back and take a look at that again if you need to. Okay, so when we actually solve these out, so this is what I always want you to keep in mind, is that we're essentially thinking about finding a volume of one of those wedges, and then the triple integral is going to integrate in all three directions, and it's going to essentially piece together all of those wedges to create our overall volume. Okay, so here's an example. It says evaluate this triple integral over B, the region B, and we've got the function e to the x squared plus y squared plus z squared to the 3/2 power dv, where b is the unit ball. And when we say the unit ball, we're just talking about a sphere centered at the origin with a radius of 1. Okay, so in order for us to convert this, the first thing is that I want to know, when am I going to convert into spherical coordinates? Well, and the answer to that is really, when is it convenient? And what I mean by that is, if I see an x squared plus a y squared plus a z squared, that's a pretty obvious situation where I'm dealing with something that has to do with the sphere. And so if I have something that has some sort of a relationship to a sphere, that's typically going to be obviously where I'm going to want to use spherical coordinates. Okay, and you'll see here that when we solve these out, when we work in spherical coordinates, when it's possible, it's really nice because these are very easy to solve. Even though it's a triple integral, we'll be able to simplify this down really nicely. Okay, so we are looking at this unit ball, and we've got e to the x squared plus y squared plus z squared to the 3/2 power. Okay, so let's think about how we would do this. So for my triple integral, here's my 3 integrand signs. I know that I'm going to have e to the x squared plus y squared plus z squared to the 3/2 power. Okay, so remember, e to the x squared plus y squared plus z squared to the 3/2, that's the same as e to the rho squared raised to the 3/2 power. So I'm starting my conversion into spherical coordinates. Now, if I'm converting from rectangular to spherical, I'm also going to have to multiply by rho squared sine phi d rho d theta d phi. Okay, so now I need my limits of integration. Remember, we're starting with the rho. So I've got this sphere that has a radius of 1. So my rho is going to go from a radius of 0 to a radius of 1. And then my theta, since we're using the entire sphere, my theta is going to go from 0 to 2 pi. I'm going all the way around the origin. And then for the phi, remember, I'm measuring from the positive z-axis all the way down to the negative z-axis. That's going to go from 0 to pi radians. Okay, so this is going to represent this triple integral. Now, here's the nice thing about this. First of all, e to the rho squared raised to the 3/2 power is the same as e to the rho cubed. But notice that there are expressions in here that have rhos, there's expressions that have phi's, and then really I don't have anything in here with a theta except for d theta. So I can actually separate this out into 3 single integrals. And this is where the advantage of triple integrals in spherical coordinates comes into play. So I'm going to start with my phi. So with phi, I know I'm going from 0 to pi. And the expressions that I have in my integrand that deal with phi is just the sine of phi. And so I'm going to separate this out because there's no interaction between my variables when I'm taking antiderivatives. So essentially, if I just treat these as 3 separate integrals, I'm not really changing anything. I'm just kind of simplifying the process a little bit by breaking these apart. So for the theta, I don't have anything in here but a d theta. And then for the rho, this is the only part of the integrand where I'm going to have to do a little bit of work here. I've got a rho squared e to the rho cubed. So that would require us to do a little bit of substitution and solve it out, but we're still going from 0 to 1. And now we just solve each one of those single integrals, and what you would end up with here is 2 times 2 pi times 1/3 e minus 1/3. And then just combine all those together and simplify, and you end up with 4 pi over 3 times e minus 1. Okay, so it's actually really easy to solve these out, provided that you've got a setup that is going to be conducive to using spherical coordinates. Okay, so there's just a quick, easy example of how these are going to work. Now, like I said, when you're dealing with the sphere, it's going to be obvious you want to use spherical coordinates, and those are really going to be the situations for us where we're going to start to involve these. There are situations where, you know, you might see an x squared plus y squared plus z squared in a different context, in a problem-solving context. And so in that situation, spherical coordinates make sense. For us, we're typically going to focus on these geometric examples, so it's going to be obvious we're dealing with a sphere. But again, from just kind of a general function standpoint, if I see an x squared plus a y squared plus a z squared, or whatever variables you have, the 3 variables squared and added together, that means that your spherical coordinates will be a good setup for that. All right, so let's take a look at another example here. So this one says, use spherical coordinates to find the volume of the solid G bounded above by the sphere x squared plus y squared plus z squared is 16, and below by the cone z is equal to the square root of x squared plus y squared. Okay, so notice we have a diagram here. And again, you're not always going to have a diagram. So the difference between having a diagram and not having a diagram is really, really big from a difficulty perspective, because if I don't have a diagram given, I've either got to visualize it or I'm going to have to graph these things out. So as best you can, try to do these by visualization, but at the beginning, you may need to actually plot these out in something like a GeoGebra 3D. Okay, so let's talk about how we would set the volume up here. Now, this is a little bit different than when we were dealing with the other setups. When we were dealing with like a triple integral and we were thinking about rectangular coordinates, we'd be looking at like basically the change in the z's. We'd be looking at the change in the x's, the change in the y's for my limits of integration. Well, remember now we have to think about what's bounding my rho, what's bounding my phi, and what's bounding my theta. Now, they already gave us some pretty easy starting points here. We know that the maximum radius I'm going to have is 4. We also know that we're going to start from a phi value of 0 and go all the way to pi over 4, because that's what the z, the lower bound for the z, is defined as. Okay, so let's set this up. So for this volume, I'm going to go straight to my spherical coordinates. So I've got my triple integral. I know I'm going to use my rho squared sine phi d rho d phi d theta. And now let's just think about what are our bounds here. So for the rho, we know we're going from 0 to 4. Remember, that's just where is this point? It's at the origin. Out to the furthest point away is 4 units away from the origin. And now for the phi, I'm going from 0 to pi over 4. And where I'm getting that is I'm measuring from this positive z-axis out to here. And so that's pi over 4 units. And then for the theta, you can see I'm going all the way around in the xy plane, all the way around the origin. So that's going to be 0 to 2 pi. Okay, so that's my setup. And again, not really that difficult, provided that my scenario is conducive to using spherical coordinates. Okay, so again, I don't have any interaction between my variables from an antiderivative standpoint. So I'm just going to break this apart. I've got an integral that goes from 0 to 2 pi for d theta. I've got an integral that goes from 0 to pi over 4 for my sine phi. And then I've got an integral that goes from 0 to 4 for my rho squared. Okay, and then from there, just solve each one of those independently. And when you do that, you would end up with 2 pi multiplied to 1 minus root 2 over 2, multiplied to 64 over 3. And again, those are all simple single integrals that you can solve. And then just combine that together to get the exact solution. 64 pi over 3 multiplied by 2 minus root 2. Okay, so not difficult to do. And again, remember, I'm not really focusing on solving these triple integrals out. I'm assuming you guys know how to do the integration steps. And especially now with these spherical triple integrals, we're breaking them into single integrals, which goes all the way back to stuff that you were doing, you know, from this perspective, essentially in like a calculus AB class or first semester of BC calculus when we just did basic integration techniques. It's not really anything advanced about what we've seen so far. Okay, so let's look at another one. It says use spherical coordinates to evaluate this triple integral. Now this is a little bit more involved because you've got a z squared here, but you can see you've got a square root of x squared plus y squared plus z squared in your integrand. So we know how to convert that. We have to remember how to convert z to get it in terms of spherical coordinates. And then notice your setup here is again given. So you can kind of see how your rho, your phi, and your theta are going to be bounded based on that diagram. So what I want you to do is I want you to take a couple of minutes. I want you to try to set this one up, and then I want you to solve it out. So pause the video, and when you come back, I'll show you the solution. All right, and here's the solution that you should have come up with for this. Now, the big thing that you have to remember is how are we going to convert and get that z squared? And remember that z is equal to rho cosine phi. So I got a rho to the 5th in here from the fact that I had a z squared. And then I also had the square root of x squared plus y squared plus z squared, which would give me rho squared. Square root of that is going to give me rho. So there's a rho cubed I essentially have now. And then the last part of that, when I do my setup, remember I've always got, when I convert to spherical coordinates, I've always got a rho squared sine phi that's going to show up in there. So that's where all these pieces for my integrand came from, was just that conversion process. And when you look at this one, again, we have this similar situation where we can break this apart. We've got a theta piece, we've got a phi piece, and we have a rho piece. None of those antiderivatives are going to interact with each other from an antiderivative standpoint. So that means I can break this apart into 3 integrals. And in the end, you get 64 pi over 9. Okay, so again, when it's convenient, the spherical coordinates can be very, very easy to work with. Now, also keep in mind, from an application perspective, we're still going to be seeing the same applications. We're going to see things with mass, center of mass, moment of inertia, same things we were looking at before, now in situations where spherical coordinates will be convenient to use. All right, let's take a look at the last thing that I wanted to talk about here, which was there are situations where you're going to have options in terms of how to set these up. And I just want to show you why, when you can use spherical coordinates, it's really kind of the ultimate best option for us when appropriate. Okay, so we have, it says a problem here that says find the volume enclosed by x squared plus y squared plus z squared equals a squared using cylindrical coordinates, and then we're going to do the same thing with spherical coordinates. Okay, so that would essentially be a sphere with a radius of a. Okay, so knowing that it's a sphere, yes, I'm thinking I should use spherical coordinates, but I want to show you the same problem using cylindrical coordinates. Okay, so let's think about how we would set this up with cylindrical coordinates. So if I'm using cylindrical coordinates, I'm going to think of this as a hemisphere. So I'm going to think about the sphere that's above the XY plane, and then I'm going to double that. And the reason I'm doing that is because that allows me to just work with a single square root instead of two square roots. And I'll explain what I mean by that in a second. Okay, so try to visualize a hemisphere above the XY plane with a radius of A. Now, if I want to get from the XY plane up to a point on that sphere, that's what's going to give me my Z limits of integration. Okay, so first of all, I'm using cylindrical coordinates. So I know I'm going to have an R, dz, dr, d theta. Okay, so you've got to think back to what we did in section 15.8. Now, from the perspective of the Z limits of integration, I'm essentially looking at R squared plus Z squared is equal to A squared. So I would solve that for the Z, and I'm going to get a plus or minus square root of A squared minus R squared. Since I'm doubling this, since I use the 2, I'm just going to go from 0 to the square root of A squared minus R squared. Okay, so that would essentially be the top half of the sphere, and I've doubled it, so I'm going to get, instead of just a hemisphere, I'm going to get the full sphere. Now, for the R values, I'm going to go from 0 to A. And then for my theta values, I'm going all the way around the pole or the origin. So that's going to go from 0 to 2 pi. Now, when you solve this out, it's a little harder here because we've got interaction between our variables. And what I mean by that is when I solve the Z part of this, when I solve the first integral, I'm going to end up with still a double integral that goes from 0 to 2 pi and then from 0 to A. And I'm going to have R times the square root of A squared minus R squared dr d theta. At this point, it just becomes two single integrals. One of them involves substitution. The other one is essentially just multiplying by 2 pi. But I've got to solve that inside integral first. We talked about that when we did cylindrical coordinates. So in the end, we know what the solution here is going to be. We'd have to solve out those two integrals. We would end up with 4/3 pi a cubed. Right? That's the volume of a sphere with a radius of A. Okay, so now let's look at the same problem from a spherical coordinate perspective. Okay, so from a spherical coordinate perspective, first of all, these limits of integration are going to be very easy because I'm just dealing with a sphere. So my rho is just going to go from 0 to A. My theta, I'm going all the way around the pole or the origin, 0 to 2 pi. And then for the phi values, I'm going all the way from the positive z-axis to the negative z-axis. That's going to give me 0 to pi. Okay, so those are my three limits of integration. And then I also know from the perspective of setting up a triple integral in spherical coordinates, I know I'm going to have a rho squared sine phi. And then we're going to have our d rho, d theta, d phi. Okay, so the nice thing here is these are all single integrals, right? So when I solve this out, I'm essentially going to go from 0 to pi. For the phi values, I'm just going to have sine of phi, d phi. And then for my theta values, I'm going to have 0 to 2 pi for my d theta. And then for the rho part of this, I'm going to have the integral of rho squared d rho, and that's going to go from 0 to A. And in the end, we're going to get the exact same thing, but we'll end up with this in a little bit easier process from an integration standpoint. So same answer, not terribly difficult with cylindrical coordinates, but it's a little bit of extra work. So when it's appropriate, yeah, sometimes you can use either one, but if you can choose spherical coordinates, if it fits your situation, you can immediately go to the three single integrals multiplied together as opposed to the cylindrical coordinates where we've got to solve that first integral and then we have two single integrals typically that we can separate out and multiply together. So it just depends on the situation. But again, when it's spherical, it's going to be pretty obvious for us because we're going to see an actual sphere involved in our process. Okay, so as you go through the homework assignment, there will be some questions where you'll start to have some options, and it won't tell you which way to set it up. And then it's going to be sort of open to interpretation. Does it seem easy with rectangular, or does it seem easy with cylindrical, or does it seem easy with spherical, or which one makes the most sense to you? Sometimes is the best way to do it. It might be harder with rectangular coordinates, but maybe it makes more sense to you that way. So that's what you'll start to be presented with as you move along through the process of solving these triple integrals in this section.